Good day and welcome back to part four of our discussion on cross products. But more broadly today, what we're going to talk about in this video will be just a summary of the two vector products that we've encountered. That would be the dot product and the cross product. So in the previous two series of videos, we've seen kind of the definition of both of these products, the various different geometric properties, as well as applications. But let's now put this all together in kind of one spot to really kind of compare and contrast the two. And if we were meeting in class face to face, this is where we'd be starting that second day of our discussion of the cross product. So going back to the dot product, let me remind you how it is defined. As long as you have two vectors with the same number of entries, that could be 2 entries or it could be 10 entries. The dot product is defined exactly the same. You take all of the corresponding entries and you multiply them together, and then you add those quantities up. So immediately note that the quantity that we get back when we calculate the dot product, this is a number, a constant or a scalar value. Furthermore, we saw that there's a more geometric definition of the dot product. If you do not have it in this component form, it is the magnitude of A times the magnitude of B multiplied by the angle between the two vectors. And this is a formula we go back to whenever we are asked to find the angle between vectors. So we always use this to find the angle between two vectors. So even though there's a corresponding similar formula for the cross product, this is the formula we will use to find the angle between vectors. It works out much more conveniently. And then in terms of when the dot product is 0, note A dot B is the number 0, if and only if the two vectors are perpendicular, or remember the fancier word, orthogonal to each other. And then we investigated a little bit into something called the projection, where we said the projection of B onto A is A dotted with B divided by the magnitude of A multiplied by the unit vector in the direction of A. And just to give you kind of an idea of what this is calculating, if you have the vector A and the vector B, the projection of A onto B, remember it's kind of the shadow that B casts onto A. So if we come down to A from the terminal point of B and hit it at a perpendicular, then the projection vector of B onto A is given here in blue. So this is a projection of B onto A, where we called this first part of it, kind of the directed length of it, the component of B onto A. That is, it measures how much of B is pointing in that direction of A. And then lastly, we finished up our discussion of the dot product by investigating an application. And the application is that work is not necessarily force times distance, but it is a force vector dotted with a displacement vector. The idea being if you have a constant force that moves an object over this vector d, this will calculate the work that is completed by that force. So that's a summary of the properties that we've seen for the dot product. Let's now dive into those corresponding properties for the cross product. So first of all, in terms of how we define the cross product, we saw an immediate difference with the dot product. The cross product of two vectors is only defined for vectors with 3 entries. So this is only for vectors with 3 entries. And the convenient and maybe more efficient way to compute this is as a 3 by 3 determinant. We put those standard basic vectors, the I, J, and K across the top row, the vector A across the middle row, and B across the bottom row. So when we take the cross product of two vectors in V3, we get back another vector in V3. Similar to the dot product, there is a more kind of geometric related property, and that property is that the magnitude of the cross product is equal to the magnitude of A times the magnitude of B multiplied by sine of the angle between. And remember what this is actually calculating. This is telling us a numeric value for the area of the parallelogram formed by those vectors A and B. And from this formula, we get a direct consequence. This sine of theta will be 0 precisely when theta is 0 or pi, which means the vectors A and B are parallel to each other. So in this case, we know that A cross B is equal to, note it's a vector, the 0 vector, if and only if the vectors A and B are parallel. And probably the most important property in terms of the one that we use the most frequently is that the vector A cross B is orthogonal to both A and B. And as a reminder, we use the right-hand rule to determine the direction of it. So if we have the vectors A and B drawn, where they have the same initial point, we know A cross B is going to be orthogonal to both A and B. And that gives us, in a sense, kind of two possible directions. To determine the direction of A cross B, we would take the fingers of our right hand, point them in the direction of A, and curl them towards B. And it has to be your right hand. Your thumb will then be pointing in the direction of A cross B. So in this case, A cross B would be orthogonal to both A and B, and pointing, I'll say it's upward here. And we find this using the right hand rule. And then our discussion of the cross product finished up by once again investigating an application. And the application that we investigated for the cross product was to look at torque. And torque is a vector which is defined to be R crossed with F. So with this kind of physical analogy of a wrench, we're thinking as R as being a vector representing the handle of that wrench, F is the force that we apply to it, and then torque is going to be a vector that gives us kind of an axis that we are rotating about. The magnitude of it is telling us the tendency of the body to rotate. So that completes our kind of compare and contrast of the dot and cross product. In the final video of this topic, we are going to look at another example and also have a worksheet for you all to work on. So stay tuned and take care.